tree is a data structure where we store data in parent-child format. It is a connected graph with no cycle. There will always be n-1 edges because there are no cycles and each node can be reached from any other node, and we have n nodes. So ultimately we need to have n-1 edges. In competitive programming, we represent tree using adjacency list. This is the tree that we have. We take n-1 edges and we update our adjacency list. See, we need to understand that ultimately we use data structure to store the data. What exactly are we going to do with that data? Well, we are going to take that data to answer some kind of queries. That's why we are storing it. We need to retrieve that data. So let's say you have a tree like this. These edges represent that there exists a relation between this node and this node. That's how we get this tree. That's how we create a parent-child format. For example, let's say this is city A and this is city B. Then here edge will represent that there exists a path or a direct road between city A and city B, right? Tree stores data in parent-child format and we want to retrieve that data. How exactly are we going to retrieve that data? We need a way to travel the entire tree. Remember, in array also we did a search. Well, how do you do a search in an array? Well, you travel the entire array. You check for every single element. That's how you retrieve data from array. So we need a way to travel the entire tree so that we can check on every single node what data we have. And there are varieties of ways we have developed to travel the tree. In this video, we are going to look at DFS and BFS. Let's start with BFS. BFS is a breadth first search. That means we are going to explore the entire tree level by level. Remember, level is the number of edges that you take to reach that particular node from a root node. For example, level of this 5 and 4 is going to be 1, level of these 4 nodes is going to be 2, and level of these 3 nodes is going to be 3, because there are 3 edges that you are going to take to reach 20, correct? So we have the root node, correct? This is our root node. Okay, how exactly BFS is going to work? Now this node is going to store two things. One is data, another information about its child, correct? So if we have the data, we can just check that data. Also, we have the information about the child as well. So what we are going to do? We are going to use this information to do next level search. See, this is the level we are currently on. We have a node here, that is a root node. It has stored the information of child. We are going to use this information and explore the next level. Now we have reached to level 1 and we have two nodes, 5 and 4. Also, this node, node 5, will also have the data and information about the child. Similarly, node 4 will have data and information about the child. So by using the information of the child, we are going to explore the next level, level 2. Makes sense, right? So what ultimately we are doing, we are using the information of a child to travel to the next level. And we are exploring level by level. So first we see 7. After that we see 5 and 4. Correct? After that we see 2, 3, 15 and 50. And after that we have 12, 13 and 20. This is the order that we visit every single node. Okay, let's try to write the code for this. As I have already mentioned, we have a start node, correct? That is a root node. I am going to put that node into a queue. Why queue though? See, queue is a first come first serve, right? That is first come first process. So we are going to use that data structure here. We will also have a vector called as visited, which is initially marked as false because we don't want to visit the same node twice. Once we visit any node, we are going to mark it as true so that it cannot be visited next time. I will tell you why exactly we need that. But let's look at this particular section, this while section. This is the main part of this BFS. Okay. So before we enter into this while loop, see what we have done here. Queue initially was empty and all the visited nodes are marked as false initially. In queue, we put the start node, that is node 7, that is a root node, and we marked it as true. So this has become true. Queue has 7 now. Then we go into the while loop. While loop checks whether queue is empty or not. That queue will be empty when all the nodes are visited. Currently, queue is not empty because we are at node 7. So we are going to take the front value that is 7, and explore all its children. Look at this. We are going to take the front value, store it into a variable. We are going to pop it. So this value is removed from Q. We have popped it, and we have stored this value into a node variable. We will print that node variable. This is the output that we have. I will write that output here. So we have cout node, that is 7, correct? Then we are visiting every single child of that particular node. It is currently 5 and 4. If that particular node, this child node, is already visited, then we are just going to skip it. If not visited, then we are going to mark it as true, and we are going to put that value into our queue, correct? So queue will have data or the nodes that we need to process. So 5 will go there and 4 will also go there, correct? This inner for loop is over. We took 5 and 4 into our queue. Okay, again, queue is not empty. So we are going to take the front value, that is 5. Remember, 7 is already popped out, correct? So we are going to take 5. Now node value is 5. We are going to print that 5 value. After that, we are going to explore all its adjacent nodes. We are going to explore all adjacent node to 5. I am referring them as a child, but they are adjacent nodes. So 5 has 2, 3 and 7 as adjacent nodes, correct? Now our queue will be updated. It will have 2, 3, but 7 will not go into our queue. Why? Because see, we are only taking the nodes that are not visited. 7 has been marked as true already. So we are not going to take 7 again here in the queue. We are going to skip it. See, we are pushing the data into queue if and only if that is not visited. 7 is already visited. So we are not going to take that. Why did we arrive at 7? 7 is an adjacent to 5. And we are taking every single value in our adjacency list, correct? Again, we will check whether queue is empty or not. Well, queue is not empty. We will take the front node. Front node is node 4. We are going to pop that node. We are going to output that node 4, and we are going to check all its adjacent node. If they are not visited, we will put those values into queue. If they have been visited, then we are going to just skip it, correct? So who is adjacent to 4? It's only 7. 7 has been already marked as true. So we are not going to put anything into our queue. Okay, so next value is 2. We are going to pop that value. We are going to output 2. Then we are going to process the node 2. We are going to explore all its adjacent, and if they are not visited, we are going to put them into queue. 5 is adjacent to 2 and 5 has already been marked as true. That means it has been visited already. So we are not going to take it. We are going to skip this particular value. Next node is node 3. So we pop that node, we print the value, and now we are going to process it. Adjacent to node 3 is 5. And 5 is already visited. It is marked as true. So we are not going to put that value into queue. And that's it. Queue is empty now. So this while loop will break. But look at this. We have visited all the nodes level by level. First we completed level 0. That is, we only have one node. That is a root node. Then we completed level 1, 5 and 4. Then we completed the next level 2 and 3. So this is BFS. Code is very simple. Try to code it on your own. Next we have depth first search, that is DFS. Now it explores data like parent, then it will go to child, then it will go to child of that, and then it will go to child, and then it will track backwards. What do I mean by that? See, we have a 7 here. It has 2 children, 5 and 4. But DFS doesn't care about all its children. What it does, picks one, that is 5. So it will visit 5. Then it will visit 2. Then it will come back to 5. Then it will visit next 3. Then it will come back 5. Now all the children of 5 has been visited. Then it will go back to 7. Then it will go to 4. Then from 4 it will go to 15. Now there are no children to 15. So it will revert back. After that it will go to 50. Now 50 has 12. So it will visit 12. Now there are no children to 12. So it will go back. Then it will go to 13. There are no children to 13. So it will go back. Then it will visit 20. There are no children to 20. So it will go back. Now all the childs of 50 have been processed. So it will go back. All the nodes of 4 have been processed. If 15 is done, 50 is also done. So it will go back to 7. Now all the children of 7 have been processed, so it will stop. It visits from parent to child, child to child, and it will keep on doing this until there are no children in this particular ancestor chain. So it will start to travel back. I hope that DFS is clear. See, BFS goes like this: level 0, level 1, level 2, level 3. While DFS, it goes like this: 5, 2, 2 to back to 5. Then we'll visit 3, from 3 to 7. Let's write the code. And as you can see, DFS code is very small because we are ultimately going to use recursion. So we are going to pass two values, node and a parent of node. Why exactly are we passing parent of node? See, when you explore the adjacency list, let's say you are at node 5, you will have 7, 2 and 3. But we are going from parent to child, child from child, child from child, right? So from 5, I don't want to visit 7. What I want to visit 2 and 3. That's why I'm passing this parent information as well. Because if the node from adjacency list is parent, then we are just going to skip it. Let's look at DFS and let's try to dry run this code. Okay, I will write a table here, node value and a parent value. Currently, our node value is going to be 7 and parent is going to be -1. Why? Because there is no parent to 7, so I'm just going to pass -1 value here and node is going to be 7. We are going to output that value of node, that is going to be 7 currently. After that, we are going to explore all the adjacent node to node 7. We have 5 and 4. So first child is going to be 5. We will pass 5 and 7 to DFS. So I'm just going to write here 5 and 7. Now when we are exploring this node 5, we are calling DFS again, correct? So now we are going to explore the node 5 because the value of node is 5 now. First we print that value. Okay. Then we explore all its adjacent nodes. 5 has 3 adjacent nodes, 2, 3 and 7. So the value of child is 7 at first. But 7 is also parent node. So we are just going to skip it. After that we have 2. Then we call DFS on 2 as well. Now you have 2 and parent node is going to be 5. In this code, we output with the value of node, which is going to be 2. And then again, we execute this loop. We check for all the adjacent node to 2. 2 has only one adjacent node, that is 5. But 5 is equal to the parent value. So we are going to skip it. There is no more adjacent node to 2. 5 was the only one adjacent node and we skipped it because 5 was parent of 2. Correct? So DFS 2, 5 is done. So this section is done. Now we go back to 5, 7. Remember, we arrived at 2, 5 from 5, 7, right? So we go back to 5, 7. 5 is the value of node and 7 is the parent. We have already explored this node 2. For 5, 7, we first explore the node 7 and we said we are going to skip it. Why? Because it's exact same value as parent. So we skipped it. And then we process the node 2. And only one adjacent node 2 has is actually 5. But 5 we skipped it because 5 was parent to node 2. Now we are again back to node 5. And node 5 has another child, that is 3. 3 is not equal to the parent. Parent was 7. So we are going to call DFS again on 3. So we are going to call DFS again on 3. So we have 3, 5. Now 3, 5. 3 has only one adjacent node, that is 5. But 5 is equal to the parent. That's why it will be skipped. And there are no other adjacent node to 3. So this loop will be over. That means DFS 3, 5 is done. Once DFS 3, 5 is done, we go back to node 5 again. And node 5 has already completed all its adjacent node. Correct? It has processed everything. So this for loop will be done for DFS 5, 7 as well. That means this is also done. We go back to node 7 and for node 7, this child is done. But there is another child. So it will call DFS on 4, 7. Correct? I will just write here. It will call DFS 4, 7. Now, let's look at DFS 4, 7. First, it will output the value of 4. After that, it's going to check for all its adjacent node. There is only one adjacent to node 4, that is 7. but we are going to not process it and skip it because 7 is parent to 4. So the processing of node 4 is also done. DFS 4, 7 is also done. Once this is done, we go back to node 7, that is DFS 7, -1. We go back to it, and there are no adjacent nodes remaining to node 7. We have already explored 5 and 4. So this for loop will be over for DFS. So this is also done. So this is how DFS works. See, it went from 7 to 5, then it went from 5 to 2. Then it came back to 5. Why? Because there are no children to 2. Then we went to the next child of 5, that was 3. From 3 we came back to 5. Why? Because for 3 there are no children. From 5 we went back to 7. Why? Because we have already processed all the children of 5. For 7 it has one more child. It is 4. For 4 there are no children. So we are just going to go back to node 7. That's how DFS works. When it comes to BFS, output was 7, 5, 4, 2 and 3. When it comes to the DFS, the answer is 7, 5, 2, 3 and then 4. So this is the traversal difference between BFS and DFS. Both of them are very important, but we are going to use DFS very heavily. Why? We have a recursion here and we visit the subtree first. See, in BFS we visited 7, then we visited 5 and then we went to 4 rather than completing this particular subtree. But in DFS, look at this. We have 7, 2, 3 as a subtree. Then we have 4 and we have this entire subtree also, which was original tree. Just to highlight why DFS is so important, BFS visits by level while DFS completes the processing of subtree first. BFS uses a queue while DFS uses a recursion. So once you found the solution for, let's say, this particular subtree, you can apply exact same solution for any other subtree. So you don't have to write that code. You can just use the process of recursion. This is the DFS code. You can just put logic what you want to put right here. And that's the main reason. See, DFS allows you to access the entire subtree easily. Compute values from bottom to top. Why it's important to compute values from bottom to top? Even though we are accessing a tree from the root node, computing the answer from the bottom is very simple because for all the leaf node there are no children, correct? So you just have to compute the value for this particular node. Then you combine that value and compute for this particular node, and thus you have solved the question for this particular subtree. You just need to extend it to others. You just write the logic, business logic here before processing the child node, or you can write the business logic here. Once you're done processing the children, then you can start processing this current node. There exists something called as dynamic programming. We are going to see it thoroughly. But dynamic programming also uses recursion and it heavily depends on memorization. So we can apply dynamic programming using DFS as well. Let's just take an example. Let's say problem statement is you need to compute the size of every single subtree in a tree. What is the size? The number of nodes that you have is called as size. For example, size of 2 is 1. Size of 3 is also 1. Because for 2, this is the subtree. There are no children. There exists only one node in subtree of 2. That is node 2 itself. Similarly, for node 3, there are no children. So size of subtree starting from 3 is just going to be 1. Size of subtree from 5 is actually 3 because there are total 3 nodes, 5, 2 and 3. For 4, obviously it's 1 because there exists only one node in the subtree of 4. For 7, it's the whole tree. So value is going to be 5 because there are 5 nodes. So this is the question that you need to compute the size of every single subtree. It is very simple. We are just going to apply the DFS. We have just introduced a new array here called as subtree, which is going to store the answer for every single subtree. So initially we have node as 7 and parent as -1. We are going to explore all its adjacent node. That means we are going to compute value for 5 and compute value for 4. Assuming that we have computed the subtree value of 5 and subtree value of 4. Let's say the subtree value of 5 is 3 and subtree value of 4 is 1. Assuming that somehow we managed to compute, we are going to update that particular value into subtree of this 7, correct? So that's how, by using the information from its children, we managed to compute the answer for 7. So if you observe carefully, we are computing answer from bottom to up. So at the leaf node, you should know the value. Then only you will be able to compute value for the parents from bottom to up, correct? You need to know the value of for the leaf node. For all the leaf node, the size of subtree is just going to be the 1, correct? And we know that because there are no children to it. You find the answer for node 7. How did we manage to find the answer for node 7? Well, first we initialize the value to 1 as a count for this. Then we said, okay, explore all its children, which is here. We said that by calling DFS, we got the answer for node 5 and we got the answer for node 4. Let's say that is 3 and that is 1. Then we are going to use these two values to compute the final value for node 7. So by using the information from the child, you manage to compute the answer for the parent. So this will keep on going. 5 will use the information from 2 and 3 and compute the answer for 5. This will keep on going. So we are computing the answer from bottom to top. We derived the formula or derived the way to compute the answer for the root node only by using the child information. So the question is, you need to have a terminating condition, and that terminating condition arrives at a leaf node. For a leaf node, there are no children, and we are computing answer from bottom to up. So you need to have answer for these leaf node, and it's obvious that we have the answer for leaf node, and that is going to be 1. So 1 will be returned to 5, 1 will be returned to 5. 5 has already its own value. So 1 plus 1 plus 1, 3. Similarly, you have 4, it's going to be 1 because it is a leaf node and there are no children to it. So we have 3, we have 1. By using these two values, we got 4 plus node 7. And that's how we get 5. So this is the beauty of recursion. You derive the value for the root node. How exactly are you going to use the information of a child to compute the answer? You can just reuse that technique or reuse that formula to compute the answer for every other node, because see, 5 is going to be root of this particular subtree starting at 5. We already know how to compute the answer for root node if you know the answer for children. 5 is a root of this particular subtree. So if you know the answer for 2 and 3, then you can compute the answer for 5. Do I know the answer for 2 and 3? As 2 is a leaf node, value is just going to be 1. Similarly, for 3, size of subtree is just going to be 1. And that's how you manage to compute the answer for 5, which is a root of this particular subtree. And from that, you can just keep on computing the answer from bottom to top. This technique we are going to use heavily. We are going to compute lot of answers from bottom to top. That's why DFS is so important. There are some mistakes that we need to avoid. This check here. See, our G is not just storing the child information, it stores the adjacent nodes. So for 5, 7, 2 and 3 all are stored. If you don't apply this skip condition, then you go from 7 to 5. From 5 you come back to 7 again. From 7 you go back to 5. And from 5 you come back to 7 again, and this will be an infinite loop. So while writing DFS code, it's very important that you pass two parameters, that is node and a parent node, so that when you travel all the adjacent node to a node, you skip the parent. You just want to focus on the children. Mistake 2 is very simple. You use BFS for subtree computation. We have just seen that DFS is very good at handling subtree problems. If you can compute the answer for a root, if you know the answer for all its children, then that means you need to apply DFS. If you know the answer for the leaf node, you can just compute from bottom to up. Third mistake is you don't understand how recursion works. Then it's very, very bad. You will never understand what DFS is, and going forward you will not understand how dynamic programming works. So it's very, very important that you know how exactly recursion works.